Let's find all asymptotes, intercepts, and/or holes and use them to sketch the following rational function. Up first, we'll find domain. To find domain, we set the denominator equal to 0 and solve. We get x equals -2. And actually, we're going to say x is not -2 because that's a domain restriction. One way to denote that is in set notation, all x such that x is not -2. An alternate way is interval notation, -infinity to -2, union -2 to +infinity. To find vertical asymptotes, we first check to see if we can reduce this rational function. So we need to factor the numerator. Two numbers that multiply to 5 and add to 6 are 5 and 1. Now look to see if anything reduces. It doesn't, so again we look at the denominator and set the denominator equal to 0. And we solve. X equals -2 is the vertical asymptote. To find holes in the graph, we look to see if any factors reduced. And none of them did, nothing canceled, so we have no holes. To find horizontal asymptotes, we compare the degree of the top and the bottom. Notice the degree of the top is 2 and the degree of the bottom is 1. If the degree of the top is ever bigger than the degree of the bottom, then we have no horizontal asymptote. However, if the degree of the top is 1 more than the degree of the bottom, like in this example, we need to look for the oblique asymptote. And we do that using division. Notice in this case, we can actually use synthetic division because the denominator is linear. So we're going to take the opposite of the number that we see in the denominator, -2, and put it in the box, and then list the coefficients of the numerator. That is 1, 6, and 5. Now doing the synthetic division, we drop down the 1, multiply, we get -2, add, we get 4, multiply, we get -8, add, we get -3. Notice in this example, we got -3 as a remainder. In the past, we always wanted a 0 remainder, but that was when we were finding zeros. In this case, we're finding the oblique or slant asymptote. We're actually going to ignore the remainder. It doesn't affect the oblique asymptote. We're going to focus on these two numbers. Those are the coefficients that we use to set up the slant asymptote. We just need to write it as y equals 1x, or just x, plus 4. And this is the oblique asymptote. To find x-intercepts, we typically set y equal to 0. Since this is a rational function, we can actually take a shortcut and set the numerator equal to 0. And I'll go ahead and use the factored version. It's a little bit quicker. Set that equal to 0. Set each factor equal to 0. And solve each of those. X equals -5 and x equals -1. So the intercepts are -5, 0 and -1, 0. To find the y-intercepts, we set x equal to 0. And in this case, to find y-intercepts, it's probably quicker to use the original because we'll get 0 squared plus 6 times 0 plus 5 over 0 plus 2. A lot of those just go away to 0, meaning we're left with 5 halves. As a coordinate, that would be 0, 5 halves. Next, we'll throw all of this together on a graph. Recall that the vertical asymptote is x equals -2. We'll represent that with a dotted line. The slant asymptote was y equals x plus 4. So that means the asymptote goes through the 4 on the y-axis. Then slope of 1. Next, we find those intercepts. The x-intercept was -5 and -1. The y-intercept was 5/2 or 2.5. And from here, we can get a rough sketch. On the right side, we've got the asymptotes and 2 points that we can go through. And then on the left side, we just have 1 point, but we do have 2 asymptotes to kind of help us get a quick sketch. If we wanted to be more accurate, we could certainly choose some values like 4, 5, 6, so on, and plug those into the function to get more accurate points. But we're going for a rough sketch here. Let's throw it into the calculator and see if it looks okay. So y equals, I'll use alpha y equals to get the fraction notation. Then we type in the numerator, x squared plus 6x plus 5 all over x plus 2. Then when we graph that, make sure it looks the same, and it looks like we're good.